Stokes' theorem. In this section, we will investigate a second higher dimension analog of Green's theorem. It's named after the English mathematical physicist George Gabriel Stokes. Stokes' theorem basically gives the relationship between a surface integral over an oriented surface and a line integral along a closed space curve forming the boundary of the surface S. Now, essentially there's going to be two different ways to evaluate and apply Stokes' theorem. So we'll just investigate both manners. Essentially, let's start with looking at a positive direction along some curve C, which is going to be counterclockwise relative to the normal vector N. Essentially, look at it like the right-hand rule that we've learned from previous sections and then from other classes. The right-hand rule basically takes the normal vector here. So we can see this normal vector coming out of the top of this thing here up top. And just kind of imagine that you're grasping it with your right hand. And as your fingers curl around the axis of that normal vector. So notice how your four fingers are curling around the axis of that normal vector. Your thumb is pointing in the direction of that normal vector. Okay? And your fingers are pointing in the direction of the positive direction of that curve itself. Now another way to look at it is if you walk in the positive direction around C, your head pointing in the direction of N, rather what's called the unit normal vector, and that'll be important in this section, so keep in mind what that is. Then the surface will always be on your left. So kind of like earlier when I spoke to you in previous sections about how it's a positive orientation if you're driving around the lake and the lake's on your left-hand side at all times. Whereas you have a negative orientation if you are driving around the lake and the lake is on your right-hand side at all times. So let me go ahead and introduce Stokes' theorem, and the hypotheses of this theorem will be very important, so please keep that in mind. So let's go ahead and let S be an oriented surface with unit normal vector N, bounded by a piecewise smooth, simple closed curve C with a positive orientation. If F is a vector field whose component functions have continuous first partial derivatives in an open region containing S and C, the surface and the curve, then this formula will be true. Now, I want to really point this out. There are two sides to this theorem here. You got this line integral, where we're going along the curve, oriented curve C, and then we have this surface integral that is going to be more geared towards the surface that the curve is being bounded by. The question is which one is better? Which side of this formula should I use? It does depend on the situation, so stay tuned. Again, the left-hand side is the line integral of the boundary C, while the right-hand side is the surface integral of the curl. Now there are actually some other useful ways to approach Stokes. So I'm just going to go ahead and list them here. I want you to notice that you can start with the original version of Stokes here, okay, which is this first here. But here's another version that you could use that would be useful. Or the surface integral, again, here is the original Stokes theorem version. But you'll notice that this other version will also be very useful. So if I were you, I'd write all these versions down, because you never know when these other versions of Stokes' theorem will become useful. So keep these in mind. Essentially, Stokes' theorem says that the line integral around the boundary curve of S of the tangential component of F is equal to the surface integral over the surface itself of the normal component of the curl of F. So essentially what's happening is the tangential component of f uh, here, okay, will be equal to the surface integral of the normal component of the curl here. Now the positively oriented boundary curve of the oriented surface S is often written as the partial of S. So Stokes could also be written like this. And as I do some examples, you'll basically take your pick. There's so many different forms that Stokes' theorem can take on. Just remember one thing. Whatever form Stokes' theorem takes on, just remember that you're really just looking for ingredients to substitute into either one of these integrals, either the surface integral or the line integral. And again, it depends on the situation, depends on what's more convenient for you. And just make sure you're doing proper substitutions. Let's get into an example. Let's go and evaluate this surface integral using Stokes. Before I get into it, though, let's kind of look at what we were given. Here's my vector field given to me. Okay. And our surface is the hemisphere, x squared plus y squared plus z squared equals 1, and z is greater than or equal to 0. That means that's just simply the hemisphere that is above the xy plane. Let's kind of just do a quick sketch of that hemisphere. Okay, so here's my hemisphere. You know, as usual, hemispheres have radii r in any given direction. And they want this thing to be oriented upward. So if you recall, your thumb must be going upward direction, going straight up. So that should essentially look like this. Notice that my normal vector is going straight up, because as you grasp the normal vector, as your fingers go around, your thumb is pointing straight up. It's no coincidence. And the reason why it's oriented upward is because the curve is positively oriented. Look how the arrows point in a counterclockwise direction around the curve in relation to the surface. Now, this is going to be our oriented surface leading us to our oriented curve. And that's going to be very important. And because we're using a hemisphere, and because also it leads us to this oriented curve at the floor, well, keep in mind that the curve on the floor here, okay, the curve on the floor is going to be a circle. So simply just replace z here with 0. You'll get that circle on the floor. So I'm going to go ahead and use the parameters x equals cosine of t, y equals cosine of t, sine of t, excuse me. And here's the thing, emphasizing the word let's use the parameters x equals cosine t, y equals sine of t. And why? Why should we use these parameters? Honestly, because I want to. It's convenient. And mainly because if you take a look at the curve at the floor here, like I said, it's going to be very convenient to use those parameters for a circle of radius 1. Now, this next portion is incredibly important, very important. Notice they're asking us to evaluate the surface integral using Stokes. So I'm going to say that again. They're asking us to use Stokes to evaluate the surface integral. Well, here's the thing. Whenever they ask you to use Stokes to evaluate a surface integral, they actually don't want you to evaluate the surface integral at all. they want you to evaluate the line integral over the curve. So I'll say that again. If they're asking you to use Stokes to evaluate a surface integral, well, you're going to use Stokes and it's going to convert the surface integral into a line integral. That's very important to point out. So I'm not really going to concern myself with the surface. What I'm going to concern myself is with the curve on the floor. Essentially, I'm going to concern myself with the boundary curve on the floor, x squared plus y squared equals 1, and z equals 0. And this is going to be true on your next exam, or excuse me, on the final exam, I guess. On the final exam, if I ask you to use Stokes to evaluate the surface integral, you're actually going to evaluate the line integral. And the same will be true if I ask you to evaluate the line integral using Stokes. It's going to take you back. So again, you'll see this more and more as we progress. So again, I'm not really going to concern myself with the surface area, the surface. I'm going to concern myself more with the boundary curve in this case. Now, once again, since our parameters are going to be x equals cosine t and y equals sine t, then the vector equation of C is simply going to be cosine ti plus sine tj. And again, don't forget where this first term here is my x term. And the second term here, of course, with the j here is where y goes. And now what you want to do is, since z equals 0, what I'm going to do is I'm going to substitute my r of t vector into f. So you remember that vector field you saw from the previous slide. So I would, if I were you, back up the video, make sure you write down that vector field f. Okay? And we're going to substitute our position vector here into the vector field itself. And again, please don't forget, z equals to 0 at the boundary curve because it's on the ground. Plug that in and we end up with this. And I invite you to pause the video here, or maybe even go back, write down the vector field, and please confirm that this is true. Also, something else we want to point out. So, and what we're just basically trying to do is gather ingredients. So once again, if we take a look at what we're trying to do here, we're trying to evaluate this here, this line integral. We're trying to evaluate this. And notice, what was the first thing I did? The first thing I did was I took my vector field, plugged in my position vector using my parameters. And that's going to give me this first ingredient here. And now I need this ingredient, my differential of r. Well, that's as simple as me taking the derivative of r. So all I simply do is take this here and take the derivative of it to get this guy. But not only do I need my vector field in terms of the position vector and my differential of r, not only do I need these two items here, you'll notice in the middle I also need to, that's not multiplication, that is a dot product. I need to dot product those two items. So let's go ahead and do that. So now that I got my ingredients there, my goal now is to take these two items, and hopefully you can see where I got them from now at this point. And we are going to dot product this with that. Now, if we recall how to dot product things, remember it's the ith term times the ith term plus the jth term times the j term plus the kth term times the k term. Now, you'll notice that the only term they have in common is the j term. This has a j term, and this has a j term, along with the dt. Okay, since they don't have an I term in common, that's going to be 0 times negative sign, that goes away. And they don't have a K term, so that's going to be e to the cosine t sine t times 0. So those are going to go away. This is going to go away. This is going to go away. You simply are going to have cosine t times cosine t, which you can imagine gives you cosine t squared. And now we just simply plug it into our line integral and integrate. Now you'll notice here that I just went ahead and gave you the answer once I plugged it in. Again, notice that t is going from 0 to 2 pi. Once we integrate, you just end up with simply pi. Remember that you'll need to find, use like a half angle identity or something here to solve this, and then you end up with pi. And I invite you to pause the video here and try to do that yourself right now. As another example here, let's go ahead and use Stokes' theorem to evaluate the surface integral. Now remember, when you apply Stokes' theorem to a surface integral, it's actually going to eventually become a line integral, as you'll see in a moment. But first, let's take a look at what we're given here. Here's my vector field here. Here's my surface S. My surface in this case is a paraboloid that lies to the right of the xz plane, and it's oriented toward the xz plane. Well, because of this, we actually have a surface that is going to be negatively oriented. And as you can see in this picture, you'll notice that here's my paraboloid, okay, to the right of the xz plane, but it's oriented toward the xz plane. You'll notice that it's oriented this way. And because it's going into the paraboloid, that means it's negatively oriented, which means that we will actually be rotating from 0 to 2 pi. Now, it's important to know why we're rotating from 0 to 2 pi. Typically, a lot of times, you think to yourself, well, of course we're orienting from 0 to 2 pi. Okay, but there's a reason why you should understand that this is actually a different situation, and you're not always going to be rotating from 0 to 2 pi. Sometimes we'll rotate from 2 pi to 0. And here's why. If we were to just focus on the xy plane, or excuse me, xz plane, where y is equal to 0, notice that when I'm orienting negatively towards the xz plane, look at these other little arrows going around the curve here. Okay, you'll notice that here, this is my positive x direction. That corresponds to this right here, yes? And you'll notice that it's being rotated up to the positive z-axis, right? And then continuing on to 2 pi, right? Well, the same thing's happening here. We start with the positive x-axis, yes? And it's rotating up to the positive z-axis. And then again, continuing on all the way around back to 2 pi. So hopefully you can see the correlation here, and you can see why we are going to be rotating from 0 to 2 pi. Now, as a little contrast, a little side note, what if my surface was oriented away from the xz plane? So here's my picture again. What if we were going this way instead? If we're oriented away from the xz plane, then that would be a positive orientation. But even though it's a positive orientation, that means our limits would go from 2 pi to 0 in this picture here. So if we were oriented away from the xz plane, in this particular case, we would go from 2 pi to 0. Now, every situation presents its own differences, but the point is, please be careful. Whether it's oriented away or toward, it doesn't matter. Make sure you know ultimately what your limits are going to be for your integration. Now, let's go ahead and go back to the original problem here. Once again, as I mentioned before, if you are asked to use Stokes' theorem to evaluate a surface integral, you're not going to actually evaluate a surface integral. You're going to evaluate the line integral. That's the whole point. So if I ask you on an exam to use Stokes to evaluate a surface integral, you actually need to evaluate the line integral. That's what you're going to be computing. So in order to evaluate a line integral, you need to focus on the curve itself. Now in this particular case, our curve is the circle x squared plus z squared equals 1. So once again, I'm going to go ahead and use my parameters to be x equals to cosine t, z equals the sine of t, which means our vector equation for c is going to be cosine t of I, the ith term, and plus sine tk. So in addition to the fact that y equals 0, where the curve is, once again, like the previous problem, we're going to go ahead and substitute in r of t into f. So I invite you to pause the video or at least go back. Try to substitute r of t into f yourself. Basically, wherever you see an x, you're going to replace it with cosine of t. Wherever you see a y, you're going to replace it with sine of t. Excuse me, z. And wherever you see y, you're going to replace it with 0. So again, x will be cosine t, z you replace it with sine of t, y you replace with 0, and you notice that you ultimately end up with cosine cubed t of k. So please go back and make sure you can verify this is true and agree. Well, as I mentioned before, not only do I need my vector field in terms of the position vector r, we also need to take the derivative of r. And so the derivative of r in this case is obviously going to be negative sine ti plus cosine tk. And then, of course, we're going to dot product this thing. We take these two items here, and we're going to dot product them. So let's recall, what is dot product? Again, it's the I term times the I term plus the j term times the j term plus the k term times the k term. Notice that they only have a k term in common. There's no I or j term in common, so the I term and the j term both go away. Basically, you simply just multiply cosine cubed times cosine, and you might have guessed we end up getting cosine to the 4th power. Then plugging into our line integral from 0 to 2 pi, cosine to the 4th power of t, end up with 3 pi over 4. Again, I invite you to pause the video and try to integrate this yourself. In this case, you might have to use half angle identity a couple times. Be good practice for you. Now, generally, there's a lot of different really powerful aspects to the Stokes theorem that really help you out when it comes to computing fairly complicated surfaces. So I want to point out this other pretty amazing and wonderful aspect of Stokes theorem. And one amazing aspect of Stokes theorem that you're going to see in just a moment here is that you could actually evaluate some sort of surface, the curl of f over some surface. Let's call it S1. Apply Stokes theorem to make it a line integral. But if the curve happens to be also very complicated, you actually can apply Stokes theorem once more to go back to a surface integral over some other surface. And the point is, as long as this surface 2 and this surface 1 both share the same boundary curve, you're allowed to do this. So once again, if you take a surface integral, you can apply Stokes to get to the line integral and then apply Stokes again to get back to a surface integral of hopefully a much simpler surface. Then it becomes a much simpler situation for you to compute. So it's another great and useful property of Stokes. And it's going to be useful when it's difficult to integrate over one surface, but easy to integrate over another surface. Again, this is very important that as long as these two surfaces, here and here, share the same boundary curve, then you are able to do this. Now, this only really works for the right-hand side or the curl side of Stokes. So just be careful with this. But You're going to see in just a moment here how we can utilize this feature of Stokes' theorem. So in this example here, let's go ahead and use Stokes' theorem to evaluate the surface integral, which again means if I use Stokes' theorem, we're actually going to convert this into a line integral. Okay, where S consists of the four sides of the pyramid with vertices, they're listed here, and that lie to the right of the XZ plane, oriented in the direction of the positive y-axis. So be oriented away from the surface itself. Notice here that our specific surface here is the pyramid, but without the base. And that C is the square base. So again, S is the pyramid without the base. S is the pyramid without this gray shaded region. It's just these four sides over here. Okay. But C is the square base itself. I'll highlight that real quick. C will be this surface going around the base here. All right. Now again, it's being oriented away from the surface in the positive y direction. And remember, once you recognize which way it's oriented, we perform the right-hand rule. And you'll notice the right-hand rule here. We hold on to that vector, and our fingers are wrapped around it in the direction of where C is being rotated. So you know C is being rotated this direction, yes? Which means, notice what happens. That means C, we must be going in this path for the line integral. But there's a problem. And there's actually quite a big problem here we have in many aspects. One problem is, you'll notice for our surface S, there's a bunch of corners. There's these lines here. That's one big problem. Okay, it's not a smooth surface. It's a surface with a bunch of folds. That's one problem, which means our partial derivatives in those cases will not be continuous. But also notice that even if we were to convert this to a line integral where we're utilizing C, you'll notice here that C has corners also. So that's going to be kind of a problem. So there is a way around this though. Let's figure that out. Since S includes all four sides of the pyramid, it's going to be difficult to integrate. But you'll notice that the base here, we have this other surface, is just a square, right? The XZ plane. So why not why not use the fact that both the pyramid and the XZ plane both share the same oriented boundary. So I want to point that out. Very important fact here. Okay. Again, notice that this boundary here, so this boundary to here, to here, to here, this square base here is the same boundary as the gray shaded region and the pyramid itself. They both share the same boundary C. And according to the hypothesis of Stokes' theorem, this means we are allowed to use, instead of using the crazy pyramid, we're allowed to use the simple square base as our oriented surface. How do we do that? We do that by applying Stokes' theorem twice. Remember, we started with a surface integral. We're going to apply Stokes' theorem once to go from a surface integral to a line integral. Okay? But then we're going to apply it a second time to go from the line integral back to a surface integral. But you'll notice this time that my surface now is not just S. My surface is S1. And we're going to go ahead and call the base of this pyramid S1, the gray shaded region. And by doing this, we will be avoiding doing 4 line integrals. And instead of doing 4 line integrals, we're just going to do 1 surface integral using the surface S1. And if you recall, now we haven't done this before in this lesson yet, but here we're going to do it now. The formula for the surface integral requires us to find the curl of the vector field, which should be easy. We've learned how to do curl in the past. And the differential of the derivative of that surface itself. Now the curl is easy. Just simply apply the previously learned formula, and I would invite you to pause the video, go back to, again, hopefully you wrote down the vector field. Please compute the curl and verify that this is true here. You should agree, hopefully. And now take the derivative of the flat surface. Now, if you take the derivative of a flat surface, it's simply going to produce the direction, in this case, that the normal to the surface itself. In other words, the differential of the surface is going to be the same as the normal of the differential to the surface. Notice that here we're talking about a vector. Here we're not. So be aware of that. In this case, what is normal to the xz plane? Well, the normal to the xz plane is simply just the positive y direction. Notice how this is perpendicular to the xz plane. In this case, it happens to be our vector j, which is a very familiar vector. Okay? And then now, what do we do? Well, again, according to the formula, what we're going to do is we're going to dot product n with the curl of f. More specifically, since n equals to j, we're going to dot product j dotted with the curl of f. So again, we're going to dot product these two items. And you'll notice that this has an I term, but this one doesn't. They both have a j term, but this has a k term, this one doesn't. So they only have a j term in common. So you will only multiply the components of the j term, which is going to be negative y squared times 1. And negative y squared times 1 is obviously going to be negative y squared, which just happens to equal to 0. Now, why does it happen to equal to 0? Well, as we already know, on the xz plane, y will always equal to 0, obviously. So that means on the xz plane, if my dot product is an expression with only y involved, we're just going to get 0. Thus, we simply plug it into our double integral, our surface integral. This is simply just going to be 0. That means this goes to 0, and the antiderivative of 0 is simply going to be just 0. Let's try another example. So we're going to use Stokes' theorem to once again evaluate the line integral. So don't forget, remember, I know I repeat myself a lot, but this simply means that we will not be actually evaluating the line integral. We're going to actually evaluate the surface integral. Now, so just again, remember that. It's going to be important for the exam. So I hope you guys pay attention to that. So I'm going to go ahead and also use a different version of the surface integral. So I'm actually going to use this version of the surface integral here. And if you don't remember where this comes from, just look back a few slides and you'll see. And in this particular case, it's actually going to make our life a little bit easier. So, and also from methods from chapter 12, we will also need to know what is the equation of this triangle itself. Now the triangle is obviously limited, but it comes from this plane, and hopefully that shouldn't be too hard for you to find. So I invite you to pause the video here and make sure you remember how you get from this triangle to this equation of the plane. And essentially we need these two items to move forward. So once again, we need this equation of the plane, and we also need the fact that we're going to use this version of the surface integral. Now, the reason why I want to use this version of the surface integral is because I want to find the normal to the surface. We want to find the normal to the surface. In this particular case, you can find the normal to the triangle if you find the normal to the plane itself. And that is also from previously learned sections. So again, pause the video here and go ahead and find out what is the normal to the surface. But also, guys, keep in mind, I don't want just the normal, I want the unit normal. So the unit normal to the triangle is going to be this, and hopefully that makes sense. And if you remember these things that we learned from previous days, from previous sections, and you recall how to find the normal to the surface, then finding the unit normal is easy because obviously you only have to divide by the magnitude, which in this case is 3. And then of course finding the curl is very simple. Just follow the formula for the curl, which I think we all should know how to do as well. Okay. And yes, of course, we're going to go ahead and dot product those two. But before we do, I want you to remember one important thing here. Our parameters here are going to be x equals x and y equals y. Therefore, our surface S is going to be z equals to 2 minus 2x minus 2y. If you simply go back to the previous slide, you simply solve for z. And the reason why I'm bringing this up is because not only will I need that for us to plug back into the double integral, but also you need to account for this differential, the differential of S, which is simply going to be the cross product of the partial derivative with respect to x of z and with the partial derivative with respect to y of z, dx dy. And again, I invite you to pause the video, find the partial of this with respect to x, then the partial of this with respect to y, cross product them, and you should end up with 3 in this case after you take the magnitude. And of course, dotting the curl of f with n, we get pretty easy. Just simply get the 1/3 just kind of comes out. We get 2x plus 4z minus 2y. Remember, I do not want z involved because it's only dx dy. It's not dz. So I need to replace z with the relationship that we have from before. And once I clean it up, plug in for z, clean it up, we simplify, obviously, then we end up getting this as our curl of f dotted with the unit normal. Then, of course, substituting all ingredients with ds equals to 3 dx dy, we now can compute. Okay? So obviously the curl of f dotted with n is going to be this up here. And ds is right here. That's going to be replaced here. Okay. If you're wondering where the 1/3 went, the 1/3 in this curl of f dotted with n canceled out with the 3 in the ds. So that way there's no more 3, and we're left with just 8 minus 6x minus 10y. Now I'm going to go ahead and do dy dx instead of dx dy. You can do it either way you wish, but you'll see that if you collapse it down, you're going from 0 to 1 minus x, and then 0 to 1. And a way to see truly how you're doing this is simply set z equal to 0 as you've done before. Okay, so again, to get these limits, I invite you to pause the video here. If you're wondering how I got the limits, I went ahead and set z equals to 0, because now we're just looking at its projection onto the xy plane. And you really do have a choice. You could do dx dy or dy dx. I'm choosing to do dy dx. Draw the picture of the triangle on the xy plane, and you'll see very easily why I get these limits with dy dx. And I truly hope you pause the video here and try to see for yourself why I get these limits. If you don't, you're not practicing, you're not recalling, and that's going to prove detrimental on the final exam. So please make sure you pause the video here and try to make sure you verify why these limits are what they are. Okay, and then obviously at this point, you know, it becomes child's play. This should be easy for you. You should end up doing this yourself, and you get 4/3 as your answer. Okay. Now the problem here again, we are going to be looking to evaluate the line integral, but since we're using Stokes' theorem, once again, we're actually going to be computing the surface integral. So we need the curl of f dotted with the unit vector again, excuse me, the unit normal, I should say. In this particular case, our plane we're talking about here is x plus 4. And since this is our plane, then the unit normal is going to be 1 over rad 2, which is pretty obvious, of negative I plus k. Okay, also the curl in this case is going to be 5i plus 2j plus 4k. Again, just following the formula. And then obviously dotting these would be quite simple. If we dot these, you'll see that we end up just simply getting negative 1 over rad 2. So now we go ahead and plug this into the line integral, which becomes, again, apply the Stokes theorem. And we end up getting that negative 1 over rad 2 is that curl dotted with the unit normal. And you might wonder, like in the previous example, I went ahead and I evaluated ds. You might notice I didn't evaluate ds this time. And the reason why I didn't evaluate ds this time is because whenever you end up with just a constant left over after you dot something, you'll notice what we have here is we have a double integral over s ds. And this should look very familiar to us. Whenever we take the double integral over a surface integral, so over s, excuse me, ds, what do you recall this is? All this simply is going to be is the constant's just going to get pulled out. So here's the 1 over rad 2 and the negative. It's just simply the surface area of whatever you're dealing with. In this case, it's a planar eclipse, because obviously it's a plane that's cutting diagonally through a cylinder. That's going to create a cross section of a planar ellipse. So now, if you are unaware or if you've forgotten that the double integral over s ds equals to just the area of whatever you're dealing with, then I would invite you to go back and look at some old notes and see that, again, don't forget, I'll just kind of write a reminder here of what we learned before. We had a formula something like this, and that's essentially what we have here. And just in this case, the surface area just happens to be a planar eclipse. And basically, no integration is needed. All you simply have to do is find the dimensions of the planar eclipse. And recall that the area of any ellipse with semi-axes A and B is simply going to be pi AB. And you might be wondering, well, wait, how did you even get those dimensions? How did you get, fine, I understand the pi, but how did you get the 2 and the 2 radical 2? Well, to find the equation of the ellipse in this particular question, simply just find where z equals x plus 4 intersects with x squared plus y squared equals 4. And that's just a pretty basic algebraic problem to do. And then you can go ahead and distinguish the dimensions of this particular ellipse. Let's try a slightly different problem. Let's go ahead and just verify that Stokes' theorem is true for the given vector field F and surface S. Now, here they give us the vector field, and the surface is the part of the paraboloid that lies above the xy plane. It's oriented upward. Okay, obviously this is pointing down, opening downward, but it's oriented upward. If we recall what that means with the right-hand rule. Now, whenever they're asking us to verify that Stokes' theorem is true, what they're essentially asking you to do is to find both the line integral and the surface integral. That's how you verify Stokes. So we actually have to go in both directions and compute both of these items. So let's go ahead and first find the line integral. So we're going to note that the boundary C is the circle, and it might be a good idea to sketch these out if you wish. This would be a pretty easy sketch since I did it earlier. So we're going to note that the boundary is where we set z equals to 0 because it's going towards it's above the xy plane, and it's going to be oriented counterclockwise as viewed from above the xy plane. Now in this case, that means our position vector will be 3 cosine ti plus 3 sine tj, a very familiar sight. And if we take this in and we actually plug it into our vector field, and let's recall that in this case, we're looking at on the xy plane, so z is going to be equal to 0. So anywhere you see a letter z in your vector field F, that term will disappear. So in this case, you plug in our value of x here, which is going to be 3 cosine t. Our value for y will be 3 sine t. So if you take those two items and plug them into the previous slide's vector field, we end up with 9 sine ti minus 18 cosine tk. Now we go ahead and dot it with the derivative of r. So again, take the derivative of r, which would be very easy to do, dot it with our vector field, evaluate it at the position vector, and I invite you to pause the video here. You should be able to get negative 27 sine squared t. So we go ahead and plug it into our line integral. We're going to go ahead and evaluate that first. Here's the dot product. There it is. Obviously, we're going to do a full rotation, 0 to 2 pi. Pretty easy integration. You'll probably have to integrate this using some sort of half-angle identity or whatever. Should end up with negative 27 pi. And since we're actually going to be evaluating Stokes' theorem, we should get the same answer in either direction. So let's go ahead and evaluate the surface integral. Now, pretty easy to see that the curl of the vector field is going to be negative 4i plus 6j minus 3k. And we're going to get a cross product here. If you take the partial of r with respect to x, cross with the partial of r with respect to y, you end up with 2xi plus 2yj plus k. Okay, that's going to give us our normal vector. Go ahead and dot those. So it's pretty easy to see. Negative 4 times 2x gives us the negative 8x. 6j times 2y is obviously going to be the 12y. And the negative 3 times 1 is obviously negative 3. Because they're dotted, there's no longer any vectors needed. And I recommend highly to use cylindrical coordinates here. Once you use cylindrical coordinates, you'll see that you also get negative 27 pi, which verifies that Stokes' theorem works and is true in this case.